Hi, good evening to all of you guys. Am I audible?
Yes, you're audible.
Okay, yeah. Thank you guys. Let me share my screen. Okay, so I hope my screen is visible to all of you guys, right? Yeah. Okay, guys, so let's start with the session. In the last session, we have discussed the basic architecture of a neural network. That was nothing but the artificial neural network, ANN. And we saw how you can design a typical neural network using the deep learning libraries like Keras and TensorFlow. Same to you guys. Happy Vinayak Chaturthi to all of you guys. Okay. So today I will discuss one more application of the neural network, that is the RNN. That stands for the recurrent neural network. So basically, RNN is the basic neural network which is used in different kinds of the generative AI techniques. So you name any of the generative AI techniques at the backend, the structure or the typical neural network working as a RNN. Although we have a different versions, or you can say different kinds of a network with respect to the RNN, but it is the one of the basic neural network which is used when it comes to the generative AI applications. So the most popular application of the recurrent neural network is basically, it is used in a time series forecasting. Time series forecasting. We also have this particular concept of the time series forecasting in the machine learning part. So those who have an idea of the time series forecasting with respect to the machine learning, those guys can relate. So there we have a models like, can you guys name it? One or two time series forecasting models which are used in a machine learning? If you guys know, you can write it down in the chat box or in the comment section. So the models were like ARIMA, Arimax, we have a something called as a Serimax. So these are the couple of popular machine learning time series forecasting models. Apart from that, there we have a something called as a Holtz-Winters method, right? So these were the time series forecasting techniques which are used as a machine learning models. When it comes to the deep learning part, we have a something called as a recurrent neural network, or RNN. So one of the most popular application of RNN is doing the time series forecasting. The other most commonly used application of the RNN is basically over the text data, that means text modeling, which is nothing but the text data analysis. So this is something with respect to the deep learning, not with respect to the machine learning. So when it comes to the analyze the text data and build a deep learning based models, and this is something called as a deep NLP. So whatever NLP we have studied, like natural language processing, that was with respect to the machine learning. When it comes to the deep learning part, it is called as a deep natural language processing, deep NLP. In short, DNLP, which is nothing but the application of NLP using the deep learning. And here comes the role of the RNN. And there are a couple of versions of this RNN, or you can say some advanced techniques with few modifications in the basic structure. Those techniques are also helpful in this particular part. That's nothing but the deep NLP. So let me give you an overview idea. What is this RNN and how you can relate it to the different kind of concepts. So actually, this concept of RNN is something related to our brain's functionality. So if you recall the first session of this deep learning introduction part, so there also we have discussed how a typical neuron works. So the working of a node or neuron in any of the neural network architecture is exactly same as the working of the neuron in our brain. So this RNN is also related to the brain's functionality. Let me just explain you how. So guys, this is the cerebrum part of our brain. In our brain, we have a 2 or 3 major parts. So one of the parts is called as a cerebrum. So this complete part of the brain is called as a cerebrum. And within this cerebrum, we have 4 important lobes or areas. So this particular section is called as a frontal lobe. This is something called as a frontal lobe. This part is called as a temporal lobe. This is something called as a parietal lobe. And this small section is called as a occipital lobe. So we have 4 lobes in our cerebrum: temporal lobe, frontal lobe, occipital lobe, and parietal lobe, right? And then we have something called as a cerebellum, which is another important part of our mind or brain, right? But let's focus upon these 4 parts, which are the frontal lobe, temporal lobe, occipital lobe, and parietal lobe. So when it comes to the deep learning, we have 3 important neural networks. One is the ANN, artificial neural network. Then we have something called as a RNN, recurrent neural network. And then we have something called as a CNN, convolutional neural network. And if you recall the introduction of the deep learning part, so there we have discussed like, so ANN, this kind of neural networks are used for a regression and classification related models. Regression or classification models. RNN is something which is used for time series forecasting, as well as over the you can say that NLP part, which is the text analytics, or better to call as a deep NLP part. And CNN, which is a convolutional neural network. So these kind of neural networks deals with the image or video data. So if you want to analyze the image or videos, so there we have something called as a convolutional neural networks, image or video data. So if you relate these 3 basic or typical neural networks model with the functionality of our brain, so you can find out that whatever we have something called as a temporal lobe in our cerebrum part, the functionality of temporal lobe is similar to the ANN architecture. Or you can say in a reverse manner, the ANN architecture is very much similar to, by saying architecture, I mean the functionality is very much similar to the temporal lobe. Why? Because in ANN, what we do, we take the huge amount of the historical data or past data, and based upon this huge amount of past data, we decide what decision to be taken in future. This is the functionality of the temporal lobe. So in our mind, based upon our past experiences, and this past experiences comprises it includes the experiences from number of past years. So based upon our past experiences, we decide what to do, what not to do in a particular situation. This is very much similar with the ANN, or you can say ANN functionality is very much similar to the temporal lobe. Now, if you see this frontal lobe, so in the neural network, we have something called as a RNN, recurrent neural network. So actually the functionality of RNN is very much similar to, or you can say the functionality of RNN can be linked to the frontal lobe functionality. So RNN can be linked with the frontal lobe functionality because RNN, it considers the short-term memory. That means the experiences which happened in past couple of you can say minutes or seconds. That means very recent experiences. So the memory is something called as a short-term memory. It won't consider the you can say very past couple of most of the time data. So it will consider only short-term data. And this is the functionality of the frontal lobe. Frontal lobe also considers only the current experiences or current scenario, and based upon that only, it will decide what to do. So the functionality of RNN can be linked with the functionality of the frontal lobe. Then we have something called as a occipital lobe. The functionality of occipital lobe is that it will recognize the images or videos what we saw in our day-to-day life, and whatever images or videos we saw, based upon that it will do the processing and it will pass the signals. This functionality is incorporated with the neural network model called as a CNN. So this CNN functionality can be linked with the occipital lobe functionality, where we analyze the images or videos. So this is how you can link different types of the neural networks with our functionality of our brain's part. So temporal lobe is linked with the ANN, RNN is linked with the frontal lobe, CNN is linked with the occipital lobe. Now, apart from that, the one part is left, that is something called as a parietal lobe. So this part is till date is unexplored. The reason is, let me tell you. So first of all, let's see this particular thing. So as I told you, temporal lobe and ANN, the functionality is same. So temporal lobe might be linked with the ANN with its main contribution, because both of the part is taken huge amount of the past data to decide what decision to be taken in the future. RNN is linked with the frontal lobe. RNN are like short-term memory. They are like short-term memory. And you will learn that they can remember the things that just happened in a previous couple of observations. Right? And based upon that, they apply the knowledge in the going forward. So this particular functionality is done by the frontal lobe. And this is the functionality is done by the RNN also, which is the recurrent neural network. And then occipital lobe and CNN, as I told you, it is responsible for the computer vision, recognition of images, objects, videos. So we can link the CNN with the occipital lobe. So the same thing is done by the CNN, which is a convolutional neural network. And then, as I told you, the fourth and the last lobe or this particular area is under exploration. So parietal lobe is responsible for the sensations, perceptions, and constructing a spatial coordination system to represent the world around us. So till date, we don't have any kind of a neural network architecture which can replicate these functionalities. So this particular area is actually under exploration, right? So in that way, you can link the neural network architectures with our brain's functionality. Now let's see the RNN, which is a recurrent neural network, and let's try to understand the architecture of the recurrent neural network. All right. Before moving to the further slides, let me just take a couple of questions if you have. So, okay. Okay, no questions. Good. So let me share my screen. I hope my screen is visible to all of you guys. Okay, guys. So let's try to understand the RNN architecture. And we'll start from whatever typical architecture we saw when it comes to the ANN. So let's suppose I have this kind of a typical neural network architecture. All right. Now, can you guys tell me how many hidden layers are there in this particular neural network architecture? Can you guys write down your answer in the comment section? No, it's not 4. I'm asking how many hidden layers are there? Exactly, it's 1. So if you recall the previous session, so there I told you the first layer, this one is a first layer. The first layer will always be the input layer. Last layer will always be the output layer. And the layers between input and output, those will be the hidden layer. So here we have only one layer which is in between input and output. So in that way, we have only one hidden layer. And within this hidden layer, we have 4 nodes or 4 neurons, 1, 2, 3, and 4. Okay. Can anyone tell me how many weights are adjusted between input layer and hidden layer? We have done the number of weights calculation in the previous session. So if you guys can calculate, you can write on your answer in the chat box or a comment section. So number of weights calculation between input layer and output layer. Anyways, let's proceed. So guys, this is a typical neural network. You can say it is an artificial neural network. And from this, how can we generate the RNN, which is a recurrent neural network? Let's understand step by step. So this is our typical neural network where we have one input layer, one output layer, and one hidden layer. Now see, just follow couple of steps. So the first step is just squash the network. How you can squash the network? Just imagine that you are looking this network from underneath. That means if you see, let's suppose you are seeing this particular neural network just underneath of this particular input layer, underneath of this particular connections, underneath of this particular hidden layer, and underneath of this particular output layer and this connection. Since all of these are one above another, so if you see from the underneath of this particular neural network, what you can see, if you see only this input layer, so rather than seeing the 3 nodes, you can see only 1 node, right? Although there are 3 input nodes, but if you see from the bottom or from the underneath of this input layer, you can see only single node, because each and every node is just above on the top of one another. And if you see the same thing for this hidden layer, rather than seeing the 4 nodes, you will see only a single node, although there are 4 nodes. Same for the output layer, right? So if you see this particular neural network from underneath, you will see the networks like this, and the connections you will see like a mesh. So here you are seeing only single input node, single output node, sorry, hidden layer node, and single output node. But it is not only 1 node. There are 3 input nodes, 4 hidden layer nodes, and 2 output nodes, right? And then just do one thing. Represent this particular connections as a single connection. So if you represent this mesh of the connection as a single connection, the network will look like this one. Again, I'm repeating, this is not a single input node. This is not a single hidden layer node. This is not a single output node. In actual network, we have a 3 input nodes, one on the top of another. And here we have a 4 hidden layer nodes like this. And here we have a 2 output nodes. And this one single connection is actually, it is a connection to all other possible nodes, right? So we have just squashed this network. And then it is a standard to represent the RNN network in a vertical diagram. That means in a vertical fashion. So just rotate this one in a vertical manner. So there you will get this kind of a notation. So that's a standard representation in a vertical fashion. So if you see this vertical network, the bottom node is nothing but the input layer. And this is not the single node, right? So we have a number of nodes are there. So in our case, we have a 3 input nodes. The topmost, this particular layer is called as the output layer. And again, this is not a single node. We have a, in this particular architecture, we have a 2 nodes. And in between input and output layer, we have a hidden layer. I'm sure up to this part, everyone is following, right? Don't worry, guys, you will get all these materials and notes. Don't worry about that. Okay. So this is what we have a vertical representation of this network, and then do one modification with this network. And the modification is, since the network is a recurrent neural network, it is a recurrent neural network. So the meaning of recurrent is, we are considering the past context also, past input also, right? So how we can incorporate the past information with the help of the loop. So just incorporate this kind of a loop in the hidden layer, because all the processing are happening in the hidden layer only. So what hidden layer will do? It will process the information and it will forward to the next layer nodes, as well as it will keep the same information with itself, so that it can consider the past context or the past information also. So this is the meaning of the word called recurrent. Right? And then since we have a architecture in a form of the neural network, so it is called as a recurrent neural network. So with this modification, you will get the standard notation of the RNN or recurrent neural network like this. Now, in this architecture, what you need to remember, the bottommost layer is the input layer. This one is the input layer. Topmost layer is the output layer. And in between, we have a hidden layer. And this is not only single node, we have a number of nodes present at each and every layer. And what is the meaning of this particular feedback or loop? So this feedback, if you see, it is connected from hidden layer to the hidden layer. It is coming out from the hidden layer and it is going into the hidden layer. That means hidden layer output is connected to the hidden layer node, or like the next hidden layer node. So you can expand this network like this. So this network is being expanded like this. Just unroll this network. So what you can get, since you have a number of nodes at the input layer, so rather than having a single node, representation like this, just unroll this network. So you have a multiple hidden input layer nodes. You have a multiple hidden layer nodes. You have a multiple output nodes. So just expand this network and you will get like this. So you can see here, we have a multiple input layer nodes. We have a multiple output layer nodes. We have a multiple hidden layer nodes. And since it is a recurrent neural network where the output of one hidden layer is becoming the input of the next hidden layer node. So if you see, from the first layer, the output of this hidden layer will go to the output layer of output node of this current layer, as well as input to the next hidden layer. So that is the meaning of recurrent. In the next layer, what will happen? This particular hidden layer will consider the current input as well as the past information coming from the previous layer. So in that way, it will consider the current information as well as the past information also, so that it can give you a better prediction. So this is the architecture we have for RNN. So just unroll the temporal loop and represent the RNN in the new way like this. Now each circle represents not only one neuron, but whole layer of the neuron, right? So whatever you saw a circle like this in the previous slide, so that was not a single neuron, but it's a actually whole layer of neurons. So this is the architecture of the RNN, right? Okay, so up to this point, let me just check if you guys have any doubts or queries. Guys, tomorrow will be the last class. I hope, I think tomorrow is the last class for this particular training session. So Friday's material, I guess it has been uploaded, and if not, it will be get uploaded by tomorrow. Don't worry about that. Okay. The certificate you will get after the completion of this particular training program. Don't worry. Okay, so let me share my screen again. I hope my screen is visible to all of you guys. So if you're clear with this RNN architecture, let me just show you a couple of applications of this RNN, the applications of this recurrent neural network. So there are a couple of applications, and these applications are categorized as a one-to-many kind of a mapping, many-to-one mapping, and many-to-many mapping. All right. So if you see the example of one-to-many mapping, this kind of application. So one-to-many is nothing but where you have a only one input, but you have a multiple outputs. One-to-many, one input and many outputs, multiple outputs. So how your architecture will look like? So you have a only single input node, and you have a couple of hidden layers node, and you have a couple of output layers. So this is the example architecture of the one-to-many. And in real time, if I talk about the example, so let's suppose you have this image as an input. That means in the input, we have a single image. And just by analyzing this input image, we are generating the text as black and white dog jumps over bar. So if you see here, we have only single image as an input, but what we are generating couple of words, or you can say a sentence, and in the sentence we have a number of words. So each and every word is an output from a one output node. So this black is an output of this first output node, and is the output from the second output node. White is the output from the third output node, and so on. So from the single input image, we are generating multiple output words. That's nothing but a proper sentence. So black and white dog jumps over bar. Right. So this is the example of one-to-many network, where we have a one input layer and multiple output layers. Let's see other application. Okay. There is something called as a many-to-one application of RNN. In the many-to-one, we have a multiple inputs, but only one output. So one of the application of this many-to-one mapping is sentiment analysis. When you have a lot of text, such as a customer's feedback or review, you need to gauge what's the chance that the feedback is positive, how positive or negative, or how negative it is. That means we are getting a feedback from the customer in form of the sentence, where we have a couple of words. So each and every word is a one input, right? So each and every word is a one input. That means we have a multiple inputs. So just by analyzing these multiple input words, we need to give the output whether this particular feedback is a positive or negative. That means my output is only a single word, but my input is a sequence of words. That is the example of many to one mapping, right? Okay, for example, let's suppose we have a input sequence like thanks for a great party at the weekend. We really enjoyed it. So each and every word is a one input for this particular network. And by analyzing this particular sequence of words, we are just generating a single output, like whether it's a positive or negative. And then we can calculate how positive or how negative it is. So this is a typical example of many to one mapping. Then many to many mapping, where we have a multiple inputs and multiple outputs. So one of the most commonly used application of this particular mapping is machine translation, just like Google Translator. So what is a machine translation? Where you have a sequence of words, let's say word 1, word 2, word 3, word 4, word 5. Let me just take an example. So let's suppose I have a sequence of words like this is data science training program. So let's suppose I have this kind of a sequence of words as the input, and then I need to translate this particular sequence of words from one language to another language. So let's say this is in English. So from English to, let's suppose, in French or in some other languages. So that is something called as a machine translation, where you have a multiple words as the input and you're generating multiple words as the output. And actually we are transforming this particular sequence of words from one language to another language, right? So this is a typical architecture of many to many mapping. Okay. So this is one part. Up to this, I'm sure the things are clear, how the RNN architecture looks like. Let me just walk you through how you can build a typical RNN model, right? And then we'll see the basics for the chatbot. So let me share my screen first of all. Okay, guys, so I hope my screen is visible, this Python notebook. Great. Guys, is the font size is visible to all of you? Okay, I think it's better. Yeah. Okay, let me increase the font size. I think it's better now, right? Okay. Let's see, guys, how you can build a typical recurrent neural network architecture. So first of all, I'm just importing a couple of basic libraries like pandas, numpy, matplotlib. So guys, matplotlib, yeah, guys, you will get all these study materials. Don't worry about that. So guys, matplotlib is a visualization library. So under the matplotlib, we have a module called pyplot. So we are just importing this pyplot as a PLT. And I have a CSV data which is a Google stock price data set. All right. So let me just show you what is this data set. So this is my Google stock price data set, where for each and every date, we have the open price for the market. We have the highest price for a market for a particular day. What was the lowest price on a particular day, closing price, and some volume of shares. So out of all these features, the feature of consideration is this open price. So this is our target variable, and we are going to build a typical recurrent neural network architecture over this open feature. That means we are going to forecast this open stock price for a Google stock price dataset, right? So what we are doing, first of all, from this data set, we are just taking out this particular feature, which is our target variable, right? Open this particular feature. So this is, I'm calling as a training data set. Okay. So if you see the length of this target data set, so we have in total 1258 data points, right? Now, so if you recall the previous session, so there I told you, if you're going to build any kind of a deep learning or neural network architecture, so their feature scaling is something which is mandatory, right? You need to perform the feature scaling if you're going to build deep learning or AI-based neural network architecture. While in case of a machine learning, it is optional. Okay. So what we are doing, we are just importing one of the scalar, which is called as a min-max scalar. Can you guys tell me what is the name of other scaling method? So in the last class we have discussed. If you guys recall, you can just write it down in the chat window. So we are just importing one of the normalization or scaling technique, which is a min-max scalar. It is also called as a normalization. And the output of the normalization process. So this min-max scalar is also called as a normalization. And what it will do, it will transform your original data set into normalized data set, where each and every value will lie between 0 to 1. Right? And what formula it uses? So the formula which at the backend it utilized by this normalization or min-max scalar is x minus the minimum value of this x, where x is the feature. You can say xi. So each and every value of this particular feature x minus the minimum value of feature x divided by max value of the feature minus min value of the feature. So this is the formula which is utilized by this min-max scalar or normalization process. Yes, ma'am. So what we are doing, we are just importing this particular method min-max scalar, and then we are creating an instance of this method as a SC, and using this instance to apply fit_transform method over my training data set, which is nothing but my target variable. And here I'm getting the scaled output. So now if you see, this is my scaled output, and each and every value will lie between 0 to 1 only. So in that way, we have performed the scaling. You can also use the second type of a scaling method, which was the standard scalar, right? Which is also called as a standardization. So in that way, we are getting the training data set. Now, when it comes to the RNN, so here I'm going to show you one of the typical application of RNN, which is using the one of the advanced or modified model of RNN that is called as the LSTM. So LSTM stands for the long short term memory. Long short term memory. For this kind of architecture, you need to prepare your data set in a little bit different manner. So how the data set is being prepared? So let me just explain you. For example, let's suppose this is my input data. This is my input data where we have a, let's suppose values are like, let me just show you from here. Yeah. So it's like 325, 331, 329, 328, 322. And let's suppose after 322, I have a 790, 790, 793, 783, 782. So first of all, guys, you need to define, there is something called as a window size. Window size. Let's suppose I have taken window size is equal to 3. For example. So how the data preparation is done with respect to RNN is, it will take first 3 data points as the input. That means it will create a new data set like, let's suppose X1 is the new feature, X2, X3, or let me start like this. X1, X2, X3, and here we have a target variable Y. Why X1, X2, X3 only 3? Because my window size is 3. So it's up to you. What will be your window size? You can change this value, right? So let's suppose I'm taking the window size as 3. And then it will take first 3 values and it will place here in the X1, X2, and X3. So the first value is a 325. Second value, 331. I'm just taking the integer value. The third value is a 329. And whatever is the next value after this 329, that is the 328. That will be the target value, output value or the target value for this particular data set. So that's a 328. Then in the second row, what it will do? It will take the next 3 values. So after 325, what are the next 3 values? Let me just clean it. So after 325, the next 3 values are this one. That is the 331, 329, 328, and in the output, what is the next value? 322. What is the next data point? So it will be 329. Next 3 data points, which were the 329, 328, and 322. 328, 322. And for this particular data set, the output will be the next value, which is the 790. So in that way, it will prepare the data set, which is the internal data set. So if you see, guys, in each and every observation, I have a couple of records which are common, right? This is because of we have a recurrent architecture. So if you see the 331, 329, and 328 from the first record, which is the input to my second record. And from the second record, these 3 values will be the input to my third record. So this process repeats until the last data point. And this is what we are calling as a recurrent architecture, right? So this architecture needs to be there. And this is being done here. So we are creating X train and Y train. So let me recall you. Before that, we have a only single variable, which was my original target variable. And using this original target variable, which is now scaled one, I'm creating my X and Y variables. How? Based on the window size. So in total, I have a 1258 data points, right? So what I'm doing, I'm taking the window size starting from 60. That means rather than taking the window size as 3, what I have just shown you, I will take 60 data points as a window size. And the new data set, that means whatever data set we are preparing, that data set will be saved in the X train and Y train in this particular list, right? So what we are doing, we are applying a loop which will start from index position 60 and it will go up to the last data point. And we are generating the X train and Y train data set by appending the scaled data starting from I minus 60 to I. That means since I starts from 60, so the first record will be 60 minus 60 from 0 to 60. So the first record will be 60 data points starting from index position 0 up to the 59, because last index position is not included. So in total, we have a 60 data points, the first 60 data points. And corresponding to these first 60 data points, we have the output, which is at index position 60. That means the next possible output. So in that way, this loop runs, and each and every time you will get the 60 data points, next 60 data points as the input, and the next data point as the output data point. So in that way, we are creating this X train and Y train from my original data set. So it's up to you what will be the optimum window size for your data set. So what you can do, you can just change this value from 60 to, let's say, 10, 15, 20, 8, 25, right, 40, and then you can analyze the result. So in that way, we are preparing our X train and Y train from our original target variable. Now, if you see the shape of your X train, so the shape will be 1198 with the 60 features, right? And this is how my data set, new like X train data set looks like. And if you see your Y train, that means the target variable with RNN as a data pre-processing. So you need to prepare the data in the similar fashion. Now, once you prepare the data in this particular fashion, then there is something called as a reshaping of your data set. This reshaping is compulsory because RNN takes the data set in this particular shape only. What is the shape? So the shape is nothing but you need to reshape your X train in this particular manner. That means, first of all, batch size, then number of time instances. Time stamp is nothing but your window size and how many indicators you have. So we are reshaping this X train data set, what we have just prepared in the above step. And then we are reshaping it into this particular shape. What is the shape? First of all, batch size. Batch size is nothing but the number of records. How you will get the number of records in a particular data set? By the shape of 0. So if you recall, guys, the shape method will give you two things. So if you apply a shape method over any data set, so it will give you two things. One is the number of rows and number of columns. And how you can fetch only number of rows? Because you need the batch size, which is nothing but total number of records. So it's like df of shape of 0. 0 is the index position for this particular output. So in that way, we are getting the batch size of this X train, and then the time instance, timestamps. Timestamp is nothing but the window size, and the window size is exactly same as the number of columns. Because if you choose the window size 3, you will get the 3 features in your X train. If you are choosing the window size as a 60, you will get the 60 features in your X-train. So it is nothing but the number of columns for the X-train, which is the shape of 1. And the indicators are nothing but how many predictor variable or target variables you have. So I have only one target variable. So in that way, you need to reshape your X-train in the same format. So these are the two extra things when it comes to the RNN. All right. So this is what we have a data preparation part when it comes to the recurrent neural network, especially LSTM. Now we have done with the data preparation part. Let's build a model. So from the Keras layer, what we are doing, we are just importing from the Keras.models, we are importing sequential model. And under the Keras.layers, we are importing dense layer, LSTM model or LSTM layer, and the dropout layer. And we are going to build a model. So model building phase is exactly same as what we have done with the previous session. All right. So first of all, we are initializing our model as a sequential model. That means we are going to build a sequential neural network. Now at this particular time, this network is an empty network. So now we are going to add a number of layers and the nodes within this sequential network. So let's add first LSTM layer and a dropout layer. So how we are adding the LSTM layer? So guys, LSTM is nothing but it is a long short-term memory. It is the modified RNN model. Right? It is one of the modified RNN model, which is most commonly used for a time series forecasting. And this one is the basic, or you can say, what is the recurrent constant? Output of one hidden layer will become the input to the next node of the, next hidden layer. Sorry guys, there was some network issue. Just a minute. Okay, is my screen is visible to all of you guys? And my voice is clear? Okay, guys. Okay, yeah. Thank you, guys. So here we are adding a LSTM layer to our sequential model with 50 neurons or 50 nodes, and we are specifying return sequence is equal to true. That means the output of the hidden layer goes to the input to our output node as well as input to the next hidden layer node. So if you specify return sequence is equal to true, that means the output of the previous hidden layer will become input to the next hidden layer. So for next hidden layer, we have an input from the current input node as well as from the past hidden layer, right? And then you need to specify what will the input shape. So the input shape will be number of timestamps and number of indicators. That means 1. So in that way, we are adding the first LSTM layer And then we are adding another layer, which is called as a dropout layer. Now, what is this dropout layer? So dropout layer is nothing but if you see a typical neural network where we have a dense architecture. So let's suppose I have two nodes in this particular layer and two nodes in this particular layer. So what is the dense neural network? Where we have all the possible connections. So these are all the possible connections. This is something called as a dense neural network. Now, the problem with the dense neural network is it will increase the complexity of the model. That is something called as a problem of overfitting. So to reduce the complexity or the problem of overfitting, we are adding something called as a dropout layer. And within this dropout, you need to specify the percentage of dropout. That means, let's suppose I have specified here as a 0.2, which is nothing but the 20%, which is nothing but the 20%. So that means what this dropout layer will do, it will randomly discontinue 20% of the connections between these two layers, right? So it will randomly disconnect or delete 20% of connections between these layers. Okay, so this is the meaning of the dropout. So let's suppose, for example, let's say this particular connection is being removed by this dropout layer, and it's a totally random in nature. So this is the working of the dropout layer. So by adding the dropout layer, ultimately we are reducing the complexity of our model. To reduce the complexity of neural network model. And this complexity is technically called as a problem of overfitting. Right? So this is something we have a dropout layer. Now, this is my first LSTM layer. And then you can also add a couple of other LSTMs layer. So here we are adding the second LSTM layer. And in the second, third, or fourth LSTM layer, the like it's up to you how many LSTM layers you are using. Only in the first LSTM layer, you need to mention the input shape. So this is only for the first LSTM layer, right? For the subsequent LSTM layers, no need to mention the input shape of your data set. So in the subsequent LSTM layers, only you need to mention what are the number of nodes and return sequence is equal to true. And this is something compulsory for the LSTM or RNN model, right? So here I'm adding the second LSTM layer and third LSTM layer. Now there is a one more catch within this model. So let's suppose, guys, here in this particular network, we are adding the 4 LSTM layers. So let's suppose this is my first LSTM layer. Let's say LSTM1. This is my second LSTM layer. This is my third LSTM layer. And this is my fourth LSTM layer. And then I have a output layer. All right. Now, if you see from the LSTM layer 1 to LSTM layer 2, I need to mention return sequence is equal to true, so that the output of the hidden node of the first LSTM layer will become input to the hidden node for the second LSTM layer. And for this hidden node, I have an input from this particular time instance also. And the output of the second LSTM layer hidden node will become input to the hidden node of the third LSTM layer. And for this hidden node, I have an input from this time instance also. Same between the LSTM layer 3 and 4. Right? But if you see after LSTM4, I have the output layer. I don't have any hidden layer, right? So when it comes to the last LSTM layer, you need to remove or you need to ignore the return sequence is equals to true, right? This is another catch. So up to the third LSTM layer, I have specified return sequence equals to true. But when it comes to the last LSTM layer, which is the fourth LSTM layer in my case, I need to only specify the number of nodes, not the return sequence equals to true. And then after this particular LSTM layer, I have my output layer with only single node, right? So these are the few technical details with respect to the model building or adding the layer with respect to the RNN, or more specifically LSTM. Now, rest of the part is same. So up to this part, what we have done with the network architecture phase. So the first phase to build any kind of a deep learning model is the define the neural network architecture, right? So up to this point of time, we have done with the first phase, which is the neural network architecture. What is the second phase? Second phase is compilation. Compilation of the model. And the third one is the execution or training of your model. So we have done with the neural network architecture, and then we are compiling this particular neural network with the optimizer as a Adam and a loss as a mean squared error. And then the third phase is to execute or train your model. So here we are fitting my model over the X train and Y train. And what are these X train and Y train? These are the same data set what we have prepared by taking the window size, right? By taking the window size, we have prepared our X train and Y train. And then we have specified epochs as 100, batch size as 32. I have just taken some random numbers. You can change these numbers and run it accurate, and you can analyze the results. So this is what we are executing our model. And up to this point of time, we have executed our model. I have already executed this one, so I'm not going to run it again. And then once my model is ready, so what I'm doing, I'm just applying this model to another data set, which is the Google stock price test data set, right? So how I can apply? I cannot directly apply this model to my testing data set. The reason being, I need to perform all of this data pre-processing part with the testing data set, then only I can apply. Because this model only understands the data set which are in this particular form, right? So first of all, what we need to do, we need to transform our test data into the same manner what we have done with the training data. So first of all, I am just preparing my testing data set by taking the window size as a 60 in the same format, and then standardizing my data set, test data set. And here I'm creating the my X-test data set as taking the window size as a 60. And I guess there are total 80 data points are there. And then reshaping my test data set in the same format, like batch size, which is nothing but the total number of records, timestamps, which is nothing but the number of like what will your window size, and then indicators are 1. So then only I can apply my model, which is my regressor. Regressor is my model dot predict over the test data set. And after prediction, so if you see guys, this X-test is a transformed data set. So we have done the feature scaling. That means we have transformed this data set. After prediction, you need to reverse this transformation to get the original values. And that is done by the inverse transformation. So by doing the inverse transformation, I am getting the output in the original values. So this is what I am getting the prediction or forecasted values. So sorry, this one is a real value, like Y-test data set, and this is the predicted data set. So if you see here, the first actual value was 778 and the forecasted value was 772. That means very close to my actual value, right? So in that way, you will get the actual and forecasted or predicted values for a stock price. And you can better visualize it by doing a graphical representation. So this is what I have done, the graphical representation using the matplotlib.py plot. So I have just taken the actual or the real stock price for the testing data set and what was the predicted stock price using this particular LSTM model. And these are nothing but I'm just adding the title. This is the title of this particular graph, X label and Y label. What is the name for my X-axis and Y-axis? And then I'm showing the legend. So this is the legend of this particular graph. And then plt.show, which is nothing but just display this particular graph. So you can see here, the red one is a real Google stock price. So whatever red graph you're seeing, this is the actual price. And the blue one is a predicted or forecasted Google stock price. Right? So in that way, you can build any kind of a LSTM model or RNN model. Okay, so let me just check if you guys have any queries. Sir, why here regressor is used? So regressor is, I'm not using any kind of a regressor. Regressor, I'm just taking a variable name, which is my model actually. Right? It's a name of the variable. It's not a linear regressor or logistic regressor. It's not a regressor. Right? So you can take any of the name for your model. Okay, you can take the RNN one or LSTM one. I have just taken the name as a regressor. Okay. Yeah. Let me check if you have any other queries. Okay. Great. So let me share my screen, guys. I hope my screen is visible to all of you guys, right? Now, at the beginning of this slide, I have asked one question. The question was, let's suppose this is my typical neural network architecture. So the question was, in between input layer and hidden layer, how many weights are being updated or calculated or adjusted? So any answer, guys, to this question? 6, 12. Any other input, guys? Anyone? You can take 1 or 1.5 minutes. You can calculate. Okay, let me show you the calculation again. Although we have discussed this part in the previous session. So guys, if you see, for hidden layer, we have 4 nodes. And each and every node is connected to all the nodes of the previous layer, right? And in the previous layer, we have 3 nodes, node 1, node 2, node 3. That means how many inputs we are getting from the previous layer for each and every hidden node? 3 inputs, 1, 2, 3. So 3 inputs, that means 3 weights for this node, 3 weights for this particular node, 3 weights for this node, and 3 weights for this node also. So in total, how many weights are there? 3 into 4 plus. There will always be a bias to each and every node, right? So one of the bias with this node, one bias with this node, and with this node. That means 1, 2, 3, 4 weights extra. That means 3 into 4 plus 4. How much? 12 plus 4. 16. So 16 weights are being adjusted between input layer and hidden layer. All right. So I hope this part is clear to you guys. Now let's see what are the things used when it comes to the chatbot. Don't worry, guys, you will get the attendance link. Don't worry about that. Okay, guys, so we saw these examples. Now, guys, when it comes to the chatbot utilizes one of the specific application of the RNN, which is called as the sequence-to-sequence models. These are called as a sequence-to-sequence model, which at the backend utilizes the concept of RNN, which is a recurrent neural network, right? And these sequence-to-sequence models are used to build chatbot. All right. So first we will see the basics regarding this sequence-to-sequence model, and then we'll see a couple of basics related to the chatbot. So guys, this sequence-to-sequence model, they consist of 2 RNN models at the backend. One of the RNN model is called as the encoder model. Another RNN model called as a decoder model. So this sequence-to-sequence model is also called as a encoder-decoder model. Encoder-decoder model. Right? These models are used in applications like machine translation, text summarization, speech recognition, question answering system, which is nothing but one kind of a chatbot only, where you ask your specific question and based upon the historical data or knowledge base, it will revert you the answer. So this sequence-to-sequence model, these kind of models are most commonly used for a text analytics. And this is the specific application of the deep neural network. So for a deep neural network, at the backend, you can find the techniques called as a sequence-to-sequence model, right? And sequence-to-sequence model, they use encoder model and decoder models. Now, when it comes to the encoder and decoder model, you can use multiple encoders in a single sequence-to-sequence model, right? Or you can use multiple decoders also. So if I show you how this encoder-decoder model looks like, so it's like you have your input data. Now, what is your input data? Since we are dealing with the text data, so the input is nothing but it is a sequence of words. Right? Or characters. It can be characters also. So you are getting the sequence of words as an input. And these inputs, like this is the input for your encoder network. What encoder network will do? It will encode these inputs in a respective format. And this encoder network is nothing but it is a one kind of a RNN network only, recurrent neural network. More specifically, it utilizes the concept of LSTM, long short-term memory, right? The output of the encoder network is something we are calling as a hidden state. It goes to the hidden state, And the output is something we are calling as a context vector. Context vector, which is nothing but the comprised or encoded form of your input data set. And if you see, your input is in form of the text only, right? The context vector is the numerical representation of your input data, and it is in encoded format. So this is something is done by the encoder network. And what is the encoder network? It is one kind of a RNN network. Specifically, it is a LSTM model. Now this context vector goes into the hidden state, which is the input to your decoder model. What decoder model will do? It will do the reverse of your encoder network. And based upon this context vector, it will try to understand the context for this input data, and based upon that, it will generate the future possible outcome words, right? What are the most probable outcome words for which the user want to get in an answer, or user want to type it? So that is something we are getting from the decoder network. And decoder network, again, it's a one kind of a RNN network, recurrent neural network. More specifically, it is the LSTM model. All right. Okay. So this is what I have explained you. We have an encoder model, which is nothing but LSTM model or a kind of a RNN network. We have an input sequence of words here. Encoder model will give you output as a context vector, which is the numerical representation of your sequence of input data. And this context vector will become input to your decoder model. And based upon that, you will get the predicted possible output words by the decoder model, right? So if you see here, what this encoder and decoder are doing, the encoder processes each token. I'm sure you guys know what is the token. Like in the NLP, we have discussed what is a tokenization. So each and every word is called as a one token. In the input sequence, it creates a vector of fixed length, which is called as the context vector. And this vector is the numerical representation of your sequence of input data. After going through all the tokens, the encoder passes this vector, which is a context vector, onto the decoder. Right. So for decoder, what is the input? This context vector. Now the context vector is built in such a way that it's expected to encapsulate the whole meaning of the input sequence. So actually this context vector is a representation or numerical representation of your input data. And the representation is done by the encoder in such a way that most of the context or the meaning which is present in the input sequence is encapsulated with this numerical representation. And that will help the decoder to make the accurate prediction. Right? So this is a little bit technical detail related to the encoder and decoder. So as I told you, this encoder and decoder models are nothing but the LSTM models, right? So this is one typical example I have taken. So let's suppose I have a sequence of word as an input like nice to meet you. Nice to meet you. This is the sequence of word which is the input to my encoder model. So what encoder will do? It will use the LSTM model, and these LSTM models will take these words as the input. So nice is one input to one LSTM model, 2 is another input, meet another input to this LSTM model, you is another input. And then what this encoder model will do, it will generate something called as a, actually there are two states. One is called as a internal state and cell state. So HT is nothing but the internal state and CT is the cell state. What are this internal state and cell state? So internal state is nothing but it is similar to your what you have as a hidden layer, right? It's a hidden layer output. Cell state is nothing but it will try to memorize what information is available from the past, because it needs to since it is a recurrent neural network, so it needs to memorize the past context also. So for that, we have something called as the cell state. Now, these two output from the encoder will become the input to your decoder. Right? So decoder will take the context present in the input data, and based upon that, it will analyze the data and it will create the output. So if you see the output of encoder, like these values, these are discarded. The output of encoder is discarded. From the encoder, we only process or we only carry forward the internal state and cell state. Internal state is similar to your hidden state. Cell state is similar to your what you can say long-term memory. So what are the context available from the past that is being stored by the LSTM model? And decoder, based upon that, it will create or generate the output. Now, if you see for decoder, the output which is being generated at each and every node will become input to the next node or next LSTM model. All right. And at the last, we have a end of word. So this start and end is nothing but it will recognize. So this is nothing but you can say tokens which are available in the encoder and decoder, so that decoder will identify what is the starting position of the prediction and where it stops. Right? So this is how internally encoder and decoder communicate to each other. So if you see the encoder block, the encoder part is a LSTM cell. It is fed in the input sequence over time, and it tries to encapsulate all the information as we have discussed. It stores it in a final internal state, which is nothing but the hidden state. And there is one more state called as a cell state. So cell state is used to store or memorize the past information. The internal state are then passed onto the decoder part, which will use to try to produce the target sequences. This is something called as a context vector. That means context vector is being passed with the help of the hidden state. The output at each time instant of the encoder part are all discarded. So this is what I have told you. The output of the encoder part, if you see, so the output of encoder is discarded. This is not of any use. So what we carry forward from the encoder network, internal state or the hidden state and cell state output. Right? So this is the output what we are getting. So this is the encoder state. So encoder model. So from the encoder model, we are getting the hidden or internal state and the cell state, which is passed to the decoder, and the outputs are discarded. Right? Then we have a decoder block. So in the decoder block, after reading the whole input sequence, the encoder passes the internal states to decoder, which is nothing but the context vector. And here the decoder will do the prediction of output sequences. Right? So this is what decoder will do. It will take input from the encoder model as the internal state in terms of the context vector and the cell state. So cell state is nothing but the past information which is stored by the LSTM model. And then it will start producing or predicting the output sequences. So at each and every node, whatever output is being produced, that will become the input to the next node. So this output will become input to the next node. This output will become input to the next node, because return sequence equals to true, right? And then we have an end of word. So this is complete picture how it is being done. Little bit more deeper aspect. So let's suppose we have this input sequence. So what encoder will do? It will use the concept of embedding. That means transforming this data into a numerical form, and then applying the concept of LSTM. LSTM will generate internal state and the cell state. What decoder will do? Based upon this internal state and cell state, that means context vector and the cell state, it will try to produce or predict the output sequences, and each and every output sequence will become input to the next node. Since these are in word or text form, so embedding will be there to convert into a vector form. And then in the output layer, we have a activation function. So let's suppose one of the activation function is a softmax. All right. So this is a little bit more detailed explanation of the sequence to sequence model when it comes to the chatbot creation. Right. So this is the internal technical details related to the chatbot. So this is how chatbot works. So when you type any input sequence, just a minute. When you type any of your query as a sequence of words, so this is what is happening at the backend, and this is something you are getting as the output from the chatbot. Right? If it is a AI-based chatbot, right? So there are multiple kind of a chatbot. So this is something based upon like chatbots which are based upon the AI-based technique, and the technique is a sequence to sequence models. Right? So if you understood this part, so let me just give you a introduction to the chatbots. So what are the chatbots? So it is a kind of a virtual assistant system that can be built conversations with the human users. So to carry forward the conversations and to resolve the queries, we have a virtual assistant system, which is nothing but the chatbot. Building a chatbot is one of the popular tasks in a natural language processing. More specifically, deep natural language processing. You can also build a chatbot using the machine learning techniques, right? But it has been found that these are not very much intelligent. So to make an intelligent chatbot, we have a deep concept of deep natural language processing. That is also called as the AI-based chatbot. So actually, there are a couple of chatbots. One of the chatbot is known as a rule-based chatbots. Second one is a retrieval-based chatbots, and then intelligent chatbots. So let's see what are these chatbots. So when it comes to the rule-based chatbot, these bots respond to the user's input based upon certain pre-specified rules, because these are the rule-based chatbots. What is the rule? Rule is something like if this, then reply like this. If this is the query asked by the user, then reply this as the answer. This is something called as a rule-based chatbot, which are built based upon the if-then statement. While writing the rules for this chatbot, it is important to expect all the possible users' input, because if you miss any one of the rule, the chatbot will become fail, right? It will not reply anything, or it will reply something garbage value, right? So hence, rule-based chatbot do not possess any kind of a cognitive skills or a intelligence. So that's why nowadays these kind of a chatbots are not in use. Then we have something called as a retrieval-based chatbots. What are these retrieval-based chatbots? So these chatbots respond to users' input by retrieving the most relevant information from the given text document. That means when you're building these chatbots, you provide the huge corpus. I'm sure you guys understand what is a corpus. You provide a huge corpus while building this kind of a chatbot. So once a chatbot is built, and let's suppose a particular user is asking certain kind of a query. So what this chatbot will do, it will try to find out the most accurate or most relevant information from this huge corpus, and that information is being answered by this chatbot against this particular query. This is something called as a retrieval-based chatbot. The most relevant information can be determined by the natural language processing with a scoring system. So there are a number of scoring system or similarity measures. One of the similarity measures is a cosine-based similarity. Though these bots use NLP to do conversations, they lack the cognitive skills actually, but they are a little bit better from the rule-based, but not as intelligent as the AI chatbots. And then we have a AI chatbots, which are the intelligent chatbots, right? So these bots respond to the user input after understanding the input. So rather than checking the information from the corpus, they take the advantage of the corpus as well as they apply the intelligence by understanding the input, right? So these bots are trained with the ML models or deep learning models over a large training data set of a human conversation. These bots are cognitive, that means intelligence to match the human conversing, just like Amazon Alexa, right? Or Apple's Siri. These are some of the examples for this AI chatbots, right? And each and every chatbot is uses the concept or technique called the sequence to sequence models. So this is what I have for this session, guys. Let me just take a couple of queries if you have any. Okay, attendance link is already shared, guys. So if you have any queries, guys, you can put your doubts in the comment section. Guys. Okay. So guys, tomorrow will be the last session. Sumant, tomorrow will be the last session. Okay. And the topic for tomorrow is the ChatGPT. So tomorrow we will see the things related to the ChatGPT. Deepak, all of these notes or PPT will be shared in the respective portal, right? Guys, there will be no exam or to get the certificate for this particular course. It is totally based upon your attendance percentage. So I guess 60% is the cutoff. Definitely, Meghna, if you have at least 60% of attendance, you will get the certificate. Yeah, Lakshmi. So if you have attended all the sessions and if you have filled the attendance form, you will get the certificate. Don't worry about it. The team will work over that. So when you will get the certificate, so for that, over to Amar, he can reply in a much better
Yeah,
manner.
sure. So guys, don't worry about the certifications. Once we're done with the program, then probably after 7 to 8 days, we roll out your certificates via registered email ID. So don't worry about that, okay? Sir, what are the upcoming courses by ExcelR? I'm very excited. So visually, I would have to inform you that we are launching 2 programs. One is for student and faculties, and it's fundamentals of full stack development. And we're going to cover HTML, CSS, JavaScript, Bootstrap, and database connectivity in that. So I'm sharing that link with you, all of you guys. So please go ahead and register for the same. Okay. Tina, sir, I actually want you to explain it once again about the recordation. So we're done for 2 times. Just drop an email to edl@thetexter.com. Our team will check on the same and they will help you. Okay. And one more good news from the ExcelR solutions for the faculties. We are launching one faculty development program on cybersecurity, and it's going to start from 25th of the September. Time will be at 3 p.m. to 5 p.m. in collaboration with CBIT, Chaitanya Bharati Institute of Technology. Okay. So for faculties, I'm sharing that link with you. So my dear folks, please go ahead and register for the same and share that link with your colleagues in your colleges and your institutes and your universities. Okay. If you have any other question for me, please let me know. I will take it up. Okay. There's one more question, sir. On 20 September, there is a schedule of another ExcelR course lecture. So how can we join both the lectures? So for that, we are winding up our this program by tomorrow only. So day after tomorrow, we'll start with the full stack, and there is no only overlap for the same. Okay. I'm exciting for the JavaScript, HTML, CSS, other courses, sir, because this is very good session and training also very good. Thank you so much. Please send the attendance link once again. Okay, 1 minute. I'm sharing that. Okay, guys, I already showed the registration link for full stack and FDP as well, FDP on cyber security. Okay. We can leave now. Yes, if you don't have any query or question, you can leave the session and we'll meet you on tomorrow. Please be there. Tomorrow is the last session. I need few details from your side and I will explain once again regarding to the certificate as well. Okay. So for this program, there is no any project, guys, no any assessment, but you will get the assignment for your practice purpose. Okay. There is one question from the YouTube. Dear sir, please share the code for all your sessions. So whatever code is taken by the sir, we'll upload that over LMS. So don't worry about that. Okay. Sir, full stack development is the link for JavaScript. Yes, guys. So we'll cover the full stack development. Sorry, we'll cover the JavaScript part in the full stack development course. Okay, so register on the same link. Yeah, you're welcome, Deepak sir. Yeah, most of that content will be developed by the faculty, so it will be open for faculties. Kaushal Kirtanen. Yeah, guys, any another question? So, Alafati, I hope I'm taking your name up correct only, or Rohit is your name. I'm just confused on that. So, thank you so much, sir, for the visit. Well, most welcome. Could you please send the attendance form once again? Yes, of course. I'm sharing that. Okay, Rohit, thank you. So there is one good question from Mansha. Sir, full stack development course for how many days? So full stack development course will be there for 15 days and 30 hours, 2 hours per day, Monday to Friday, 7 p.m. to 9 p.m. Okay. So Sakshi Patil is asking, what is LMS, sir? So Sakshi LMS is learning management system, and we used to provide the recorded sessions, material assignments over the LMS and this ExcelR live portal. Okay. Ritika is asking, what is mean by NFDP? So N stands for National Faculty Development Program, NFDP. All materials are available permanently on portal. Yes, Sandeep, all the materials and recorded sessions will be available permanently with you for lifetime. You are asking me the topic of NFDP. So the topic will be cybersecurity. Okay. Yes, Rohit, you can leave. Guys, if you don't have any career question, you can leave the session and we'll meet you on tomorrow at same time. Tomorrow is the last day. So please be there. Okay. Okay, you have a small doubt, please let me know. So Vaishali, I also don't have exact agenda with me, but probably we'll share that by tomorrow. What will cover in the cybersecurity as well. Okay. Yes, Rohit, for sure. We'll cover the soft skills as well, but in the future, it will take you some time. Okay. Yes, Rohit, you can. It's open for all. Okay, then I hope there is no more questions. So there's one question from the YouTube. Lakshmi Dangar is asking, sir, what is the next upcoming program in the XLR? So Lakshmi, I would like to inform you that we're launching fundamentals of full stack development from 20th of the September for 30 hours. And we'll cover HTML, CSS, JavaScript, Bootstrap. Okay, so I'm sharing that link over the YouTube as well. So please go ahead, register for the same. You will get the LMS access for lifetime. Okay. Okay. Thank you, Rohit. Then thank you so much, all of you. Bye bye. Good night. Have a nice time.